Maybe I'll remember to record this time. Okay, so the capacitance total, we just add those two values together. To what? Okay, 5.1 nanofarads. With that, we can solve for our reactance total. So 1 over 2 pi times our frequency times the capacitance. And in this case, we're looking for total, so we'll use the total capacitance. So we have 1 over 2 pi times our frequency, which is 4390, and the capacitance is 5.1 nano. So what does our reactance total come out to be? Remember to use lots and lots of parentheses when we're solving for these guys. Nano's negative 9. Milli, micro, nano, pico. Okay, what angle? Negative 90. Okay, so we can go through, we can solve it this direction. The next part that we're going to run into is, let's find the individual reactance values. X of C1 is 1 over 2 pi times the frequency times capacitor 1. So we plug that in, 1 over 2 pi. Our frequency is 4390. And our capacitance of C1 is 1.8 nano. Reactance. The reciprocals, yes, because at that point it's just a resistance. At what angle? Negative 90. And that is a good catch right there. Because you're like, wait a minute, my total is 7,000, but one of these values is 20,000. But then, as you were saying, you caught it. The configuration you have. Now that we're in parallel, we're dealing with a resistance value. We just treat it like regular resistance. We'll put it in the reciprocal formula. Okay. So we've got that one. X of C2. We're going to find the same way, same formula. Only we're going to use capacitance 2 for it. So we have 1 over 2 pi times 4390 and 3.3 nano. What value do we get here? How much? 10.986 K. At negative 90. Okay, now that we've solved for that, we have it in terms of ohms, resistance. Now we can just do our regular conglomerations of these. We're going to, moving everything together. So we can do the product over the sum, we can do the inverse, and this is going to be really easy because everything's at 90 degrees, or the negative 90, that's going to maintain. So the negative 90 will maintain for the entire process. If they're out of phase, it's going to get a little bit more difficult as far as what we have to do. But since all we have is capacitors, we can just do the inverse. So we take 1 over 20, 141. Uh, 10, 986 at negative 90. So when we go through this process, we're going to follow these exact same steps. We're going to keep the angles. we're going to take the reciprocals of them. When we take the reciprocals of these guys, what we're going to see is these guys are going to flip signs. So what's the reciprocal of 20, 141? Yeah, 1 over 20, 141. What's that value? We're going to break this down step by step. 6.5 what? Yeah. You base 0, are you sure? It's going to drop at 2 orders of magnitude past that. Microsiemens. Okay? So we've flipped it into the opposite of resistance, which we're going to talk about the next chapter when we start talking about the opposites of these guys. Because just like resistance has its opposites and it's the conductance, we have another name that we can call these guys as well. And we'll talk about all that later. Yes? Huh? What number is this? We are finding the total reactance. Sorry. Yep, we're just double checking this value. So I'm just showing you the process of how we do this. So we take the inverse of this guy, which is going to give us the conductance value essentially. We're going to add that to this value. So we have the 10, 986. We inverse that one, and we get 91.025 micro. And so when we're dividing these guys, if we're not given an angle, we assume 0. Okay? So what we have here for our angle, at angle 0, so 0 minus a negative 90 is positive 90. Okay? So now we have these two values that are at a positive 90. We add these two together. Oops. Get 91.025 and 49.650. So we end up with 1 over 140.675 micro at 90. And because they're at the same angle, we can just directly add them. We don't have to convert back into rectangular. So now when we take this value, we take the reciprocal of it again. That 90 is going to turn back into the negative 90. So we've maintained that where that negative 90 is coming from. This is one thing I wanted to show you guys is these values still will translate through. A lot of times we could just skip this step because we know it's going to be negative 90 because all it is capacitors. So when we take the reciprocal of this value, 140.675 micro, what do we get? Again, both ways we do it, we come out with the right answer. Any questions about this? Okay, where did I lose you? Okay. Oh, this first one? That's our frequency. So we have 2 pi times our frequency and the capacitance. The frequency is 4.39 kilohertz, or the same as 4390 hertz. It was just easier to write that out instead of doing the decimal and the K. So we solved it using our totals, and we can also solve it using our actual values that we get, the individual reactances. And this process that we go through is what we're going to be doing when we go to series and parallel, as well as when we start adding in resistors. basically in the end, this stays at negative 90 and goes back into negative 90 when we're only dealing with capacitors. Okay, so now that we've verified that we're at least on the right track for now for getting our total reactance, we can continue to move forward. So now we need to solve for our current total. So current total is equal to voltage total divided by our reactance total, or resistance total. And in this case, all we have is capacitive reactance. So we have 5 volts divided by 7.109 K at negative 90. And the angle of our voltage is at 0 because we're not given it, so we assume 0. What does our current come out to be? .37 at a positive 90 degrees. Because again, we have 0 minus a negative 90. Okay? So we have total. What is our current going to do in this circuit? It's going to split up. It's going to divide up. So we're going to have a total of 703 microamps. So when we solve for capacitor 1 and capacitor 2, where they're in the different branches, those two better equal the 703. Okay? So the current going through capacitor 1 is the voltage of capacitor 1 divided by the reactance of capacitor 1. What's the voltage that we have across C1? 5 volts. And our X of C1 was 20.141 kiloohms at negative 90. So what does that current come out to be? Okay, at what angle? 90. Because remember, 0 minus a negative 90. Because we're dividing. If we're multiplying, we would just add them. Okay? Current of capacitor 2, voltage of capacitor 2, divided by the reactance of capacitor 2. So we have 5 volts, because again, it's in parallel with the source. And we divide that by the 10.986K at negative 90. What do we get there, Seth? I just saw you punch a number, so.
Oh, no, it wasn't.
You got it? What'd you get? Okay. These guys are at 90 degrees, so we can add them together. And what do we get when we combine these guys together? Huh? We get our I total. Okay. So now the last thing we want to do is we want to solve for power. To solve for power, what units do we need to have our voltages and currents in? RMS. What are our values in? They're in RMS. All of them are. Because when we started, we were not told if it was peak or peak to peak. And so we take that value as RMS. So then we can just multiply this. We don't have to convert anything else. Okay? So the power total is equal to the voltage total times the current total in RMS. Voltage total was 5 volts at 0 degrees. The current total was 703.375 microamps at positive 90. But when we're dealing with power, the angles go away. We don't care about the power, the angles. We just want to know what the value is. What's the magnitude of this power? Because power is power. Huh? I think so. I've never actually seen Game of Thrones, but it wouldn't surprise me if it was. Okay, so what's our power total? Okay, what type of power do we have? Remember yesterday we talked about the 3 different kinds? Close. Apparent power. Reactive power is just across the capacitors. Yep. And you are actually correct. Because we have no resistance in this thing, it is all reactive power. So in this instance, yes, it's apparent power and reactive power. Okay? Because what value is the current in? Is it peak to peak, peak, or RMS? We never modify. Reactance is reactance. It doesn't have a unit of peak to peak RMS or anything like that. It is what it is. The 90 degrees goes away. Because it's power. We don't care about the phase angle of power. Yes. Yep. So in answer to your question, so the reactance does not have peak to peak RMS or anything like that. The voltage is where we get that from. The voltage is an RMS. So if we're using this RMS value, that means this current is also going to be an RMS. So it all comes back down to what are we using for our voltage. That's where we care if it's peak, peak to peak, or RMS. But to solve for power, we want everything in terms of RMS. That way we can match between a DC equivalent and an AC load. All right, so we got 3.517 milliwatts. So what should the 2 powers add up to be? This. Because power adds regardless if it's in series or parallel. It's the total power that's used by the circuit. So every component is going to have some sort of a power that it uses. The total power is just simply adding everything up. Okay, so the power of capacitor 1 is equal to the voltage of capacitor 1 times the current of capacitor 1. So the voltage is 5 volts. The current of capacitor 1 is 248.25 micro. And that gives us how much? Okay. Okay. Power capacitor 2 is equal to the power total minus the capacitor 1, or the voltage of capacitor 2 times the current of capacitor 2. And what do both of those equal? Huh? C2, not power total. 2.276 milliwatts. They should both equal the same value. Okay, that is basic caps and resistors in parallel. So again, if we wanted to solve the same type of circuit using resistors, we would just have to stick in resistors that were equal to 10K and 20K. We would put those resistors in, we would solve for it, we would get the exact same answers except for the phase angles. They would be zero because the resistors do not react to phase angle. They do not care what frequency it runs at. That's the nice thing about resistors, is they will play nice and stay the same depending on how we shift frequencies. The rest of the components, they will react to the frequency depending on what it is. Okay, any questions about parallel circuits? I know we're covering these pretty fast because, I mean, when we were doing DC, we spent a whole week on series. We'd spent a whole week on parallel. Like I said, they are just the same. The only thing different that we're now doing is now we're introducing a varying frequency and a varying voltage. But we've eliminated the varying voltage by declaring at what point we're measuring this voltage. The peak, peak to peak, or RMS. Huh? Yeah, at the very beginning if you want to. That's just fine. If you're having to solve for powers, which you should always solve for power, especially in resistors, make sure you have a large enough resistor to handle it. Yeah, you can convert this to whatever you want, just as long as you indicate what it is. In some of the labs, people like using peak to peak. That's fine. Some people like using RMS. I pretty much use peak because it's real quick and easy to get those values. You don't have to calculate anything. Okay? Questions about this? Okay for now? Okay, it just takes some practice. Like I said, go through with the homework assignments and get through them. This, you guys now have enough for the terminology quiz, and you also have for the series and for the parallel cap. They translate, like I said, just the same over to resistors as capacitors do. You're just using your resistance value versus your reactance value. There's a lot of little steps, but like I said, they are very similar with just a small couple of exceptions. Come on, mouse. Okay, let's go through another one. We have our generator, 2 capacitors in parallel, 18 volts, 3.82 kilohertz, 15 nanofarads, and 15 nanofarads. RMS, because it doesn't tell us, so it's RMS. Yep. Does that help, Max? Okay. So the things we want to solve for is we want to solve for the capacitance total, the reactance total in kiloohms at some angle, our current total in milliamps at some angle, and the current of capacitor 1 in milliamps at some angle. Yes. So I'll give you guys a minute to work through this. Do what? This one's a fairly easy one that we can take lots of shortcuts in. Lots of shortcuts. Ninth.